Hey everybody, welcome back to Young Engineers of Today. I hope you're all interested in continuing with the bridge building software and learning some more about how it works and some of the things that you can do with it. We'll start off with some review, just really quick review, maybe like 5 minutes or so of everything we went over on Monday, and then we will dive right into the bridge building software and go from there. Now, a fair bit of warning. I have been running into visual glitches with the bridge design software, the Westpoint software, so things might look weird on my screen. I'm going to try and explain what I'm doing as best I can, but uh, there is no way for me to guarantee that it's going to work properly. There doesn't really seem to be a rhyme or reason to it. I restart my computer, I restart the program, I get rid of screen capping software that I have going on, and it doesn't really seem to cooperate. So, uh, unfortunately, that's just going to be something that I'm going to try and struggle with. But hopefully, it'll still be clear for you guys to be able to see what's going on. All right. So, we started out on Monday with talking about the forces that act upon a bridge. Namely the compression force, or the smashy force, the tension force, or the pulley force, and the shear force, or the pulling sideways force. So went over the differences with those, and I did the drawing of the tire wrench and everything like that, and it was all very uh, poorly illustrated, but on my end. But hopefully it made sense. And then we went over to the loads that create those forces. So the dead load being the weight of the bridge itself, the live load being the weight that the bridge is carrying, including people and cars and stuff like that. And then the differences in live loads, that is static and dynamic, whether or not the load is still or moving. And then we went over thermal load, which is load created by changing temperature. Super simple. Earthquake load, pretty straightforward. When the ground is shaking, that creates stresses on the bridge. Earthquake load. Similarly, the wind load is another one. The wind blowing, causing the bridge to shake, and that can be an issue as well. Then we spend some time talking about the different types of materials that bridges can be made out of. So wood, concrete, reinforced concrete, cast iron, and steel, as well as the pros and cons. Wood being cheap and it's readily available and it handles tension and compression well. On the other hand, it has a nasty tendency to catch fire. Concrete and reinforced concrete are both pretty weatherproof and fireproof. Both handle compression pretty well. However, concrete does not handle tension very well, which reinforced concrete does. Things like that. They're both pretty cheap. Cast iron and steel both have the pros that they're easy to shape into, unique forms, which can sort of improve upon the bridge building uh, science. And they're both pretty expensive, which can be an issue. Steel tends to be more weatherproof than cast iron does, and cast iron has that nasty tendency to just sort of fail without warning. So that can be a problem too. But we spent some time on Monday going over the pros and cons of all of them. Once we were done with that, we went over shapes. Bridge shapes just being like the rectangle, not very good. Arch is good for compression, and triangle works pretty well with both compression and tension. So just the different types of shapes that can be present inside of a bridge. And after that, we went over a pretty short history of bridges, from arch bridges in Rome to iron bridges to suspension bridges. And that was pretty much it, other than talking a little bit about the Tacoma Narrow Suspension Bridge, where the wind brought it down, and sort of that sort of thing. But really short history of bridges. Excuse me. Uncontrollable yawn there for some reason. Some sort of pressure change is messing with my head. Anyway, um, That is just pretty much a, hey Kai, how's it going? That is just pretty much a review of what we went over on Monday. Nothing too crazy. Uh, and we got started on West Point Bridge Designer, but we didn't really spend much time with it at all. And I kind of glossed over everything that can be done in it, so I'm going to start over pretty much from the beginning today, just in case anybody on Monday missed the lesson two. We'll start from there, and we'll go through basically building a simple first bridge as sort of a walkthrough tutorial example kind of a thing. And if there's any time left over at the end, we'll use that as open time to work on your own bridge designs, because as a reminder, there is the Young Engineers of Today Bridge Design Contest. So you have to use the 2015 software, which is fine, because you've already downloaded it, provided you've been following along in the lessons. That shouldn't be an issue. The least expensive bridge wins, and in the event of a tie, the person who submitted their bridge design earliest wins. So that is to say, if there are three designs which are tied for cheapest, the earliest submitted design will be the winner. So that's something else to take into account too. And we're going to try and announce winners by next Monday. And by try and announce winners, I believe Mr. Dubik might just send out an email with the winners, or we might announce them publicly. I don't really know. We shall see. Regardless, that's planned for next Monday. So hopefully, you can take this lesson to take something from this lesson today and use it to design a bridge by maybe the end of this week. Just as a reminder, there will be a middle school winner and a high school winner, and each of these winners will receive a $20 gift certificate to Adafruit. And the way you submit it is you post your scores in Edmodo, and you can submit as many designs as you'd like. Now, you'll have to take note of the fact that the winner will have to submit screenshots showing the number of iterations in their design. And I'll show you what that means by the end of the lesson here. So it sounds a little bit that you have to take pictures of each change in your bridge. At least that's one way it could be interpreted, but that's not the case. Thankfully, there's a very easy way to keep track of it in Bridge Designer 2015. So we'll go over that. So let's go ahead and open up West Point Bridge Designer 2015. Now, the confusing thing is this is labeled West Point Bridge Designer, but the software is just called Bridge Design. So if you start typing in West Point or trying to type in West Point, the software isn't going to show up in your search. So don't even waste your time with that. Just West Point. And, there are the tips of the day, blah, blah, blah. And like I said, I'm going to start from, square one, and we're going to work our way up from there, just in case you need a refresher from anything on Monday, or in case you missed Monday, or, because I also went through everything pretty quickly on Monday, too, at the end there. So we're going to create a new bridge design and hit OK. And it's going to start out with the design requirement. So we've got the whole thing about what you're expected to do, and that is basically to make a bridge that will not fall under its own weight and the weight of a couple of trucks, and to keep the project cost as little or as low as possible. And then you got the cross section of the river. You can see the river banks. We have to span 44 meters, and it's 24 meters above the river. So meters, it's not a one-to-one conversion, but a meter is decently close to a yard, enough that in my head I can say, hey, 44 meters is about 100 or about 44 yards, which is about 130 feet-ish. And we can probably round that up to about 150 feet to account for, the decimals and everything like that. So about 150 feet. Which is, no insignificant amount of distance to span. Keep in mind your site cost at the bottom here, and it will also show up here. This is what we're going to use to determine, who has the cheapest bridge. So, keep that in mind at all times as you're designing your bridge. Are you participating in a local bridge design contest? We are not. I mean, technically we are, but we don't have a code for that. So you're just going to keep it at no and hit next. All right, and then this is where we can really start to mess with the template, the beginnings of the bridge. For when you're working on your own design, you can add in, abutments for an arch, mess around with that, so you can strengthen the design of the bridge that way. You can add another, basically a post in order to build upon for your bridge, which might help things. Cable anchorages, so you can make your own suspension bridge. And you can even lower the height of the bridge, which involves excavating out the riverbanks in order to do that. So as you might imagine, doing all of these things is going to affect the cost of your bridge. Notice that the price has pretty much doubled from its original amount after having excavated that much. So, you want to take into account everything that you've changed. Keeping it standard abutments, no pier, no cable anchorages, 24 meters, that's going to be your cheapest starting site cost. And if you click this arrow over here, it'll give you a breakdown of where that all comes from. But who knows? That may not even equal the cheapest bridge in the end. That largely comes down to, how you design it. There's also deck material. You can use medium strength concrete or high strength concrete, and those basically just high strength concrete is thinner. It's 0.15 meters thick as opposed to 0.23 meters thick, which just basically means that this part of the bridge right here is going to be lighter because there's less concrete being used. This deck is going to be lighter. Also notice that it's going to be more expensive. So for this little tutorial bridge thing, we're going to keep everything at standard. So 24 meters, standard abutments, no piers, no cable anchorages, medium strength concrete, and standard 225 kilonewton truck. So that's everything that we're going to start out with. And then you can also select a template. Now templates are simply like this kind of stuff doesn't necessarily exist on the bridge yet. It's just a template that you can draw on top of, so you have some idea to work with. And you have the deck truss, which goes underneath the bridge deck. And then you have the through truss, which goes on top, and the truck, moves in between the through trusses. And then you have 3 of each type. You have Howe, Pratt, and Warren. And Warren, let me click on it. We're going to be using the Howe template for the through truss for this tutorial, but again, mess around with it, see what you can do. And it's going to be designed by Donald Duck. I don't know why Donald Duck, no idea, but that's just what popped in my head. Put your name there or whatever, or Young Engineers of Today. Next, click the Finish button to activate the drawing board, draw the joints, draw the members. So this is basically just telling you how to design your bridge. At that point, you can hit Finish. And it's doing the thing for me. Wonderful. Okay, so immediately, let's take note of a few things. We've got a tools box right here. It's not a toolbox. I mean, it is a toolbox, but it's also a tools box because it's a little window that's labeled tools. Yep. And then we've got this little calculator up here with our starting cost of $74,700, and that is our running cost of the bridge so far. So that is going to increase as we add more components to this bridge and make it more complex. Status right now being worked on currently. Here is the number of iterations, so you'll include that screenshot along with everything else here. We've also got the ability to start a simulation and basically run it as is, see if a truck will be able to make it across. We wouldn't be able to right now because the bridge is technically not complete. Actually, we might be able to. It might just... No, it's not. It's not complete. Yeah. We're not able to. Alright. And then over here you've got a member list, which is a list of basically all of the beams that we're going to go over, and we'll go into more detail on what's on there in a minute. But let's take a look at our tools list. We've got this gray circle. The gray circle is the node or joints tool. This allows us to add new joints to the bridge. Basically, things that we're going to connect other stuff to. And it's really easy. All you do is you just click on it, and then you click on a spot where you want to place a joint. Left click. It'll place a joint there. You might see if I click, there's nothing there, but that's because of the visual glitch that I have. If I right click, it updates, and you can see that there's a joint there. So go ahead and add some joints to all of these gray dots at the top of the bridge design. The bottom here, you'll notice there's a solid gray line here and everything like that. The bottom's actually already filled out with members and joints because it's supporting the deck. The top here, however, is not, because we can, sort of work with it in different ways and stuff like that. So we're going to select the member tool at this point, which is the one that has, you'll notice there are two circles, which could actually be two smaller joints, and then a line connecting them, and that is the member tool. The member tool allows, oh my goodness. The member tool allows us to draw basically, there we go, beams between joints so that, our bridge can hold itself up and stuff, because that's kind of important, right? So let's go ahead and notice I'm drawing them individually, but if it's a long line like this, I can draw from one end to the other. It automatically fills it in, which is pretty nice. Go ahead and draw all of these members in, just overwriting the small, thin gray lines, because again, those are members which don't exist yet. That's just a template so that you can draw upon it. And in the end, it might look something like this. Just for our first try. Later on, we'll, make it look better or whatever. But for now, this is what it looks like. We haven't talked about these other tools yet, but, let's go ahead and do that. So this cursor, is the selection tool. We can click on it. And, if yours wasn't visually glitching like mine is, you would be able to get information on it over here on this right-hand side. And then the eraser tool is pretty self-explanatory. You can erase members. Let's make sure that it's drawn. All right, it's still there. Perfect. Now, over here, mine is empty. There we go, because it hadn't refreshed yet. But under member list, you'll notice that it's been populated with a ton of things. We've got material type CS, and we got a number 1, 2, 3, 4, 5, blah 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 blah. We've got a cross section all listed as bar, size in millimeters all listed as 140, length in meters. Most of them are listed as 4, some of them are like 5 and change. Got a slenderness here. The ones that are 5 and change are apparently more slender than the ones that are 4. And we'll go over that kind of stuff in a minute too. And then you've got these ones that are all blank over here on the right hand side. You got compression force and strength and tension force and strength. And compression force and strength and tension force and strength are blank precisely because we have not simulated this yet. When it is simulated, it will give you a value from 0 to usually above 1. I've never seen it go as high as 2 before, but it's entirely possible. It might actually have gone higher than 2 in my previous classes because I wasn't paying attention to it between builds. But anyway, generally, always, you want to keep it at 1 or below. And you'll see what I mean in a minute. But now that we've gotten this built, this visually glitchy mess right here because of my computer, let's go ahead and click the simulation button and see what happens. Well, immediately our bridge does stuff it's not supposed to do. It bends downwards, and this part bends up here because there's so much force on it. You'll notice that all these bars are red right here, and these bars are blue down here. Like this one's pretty dang blue. These are fairly blue. These are a little bit blue. These are red. This one's super red, and it's bent. It's just all bad, Bridges shouldn't do this. And if we go back to the drawing board, you'll notice as I move my cursor over this and sort of correct the visual glitching, those same areas are covered with hash marks. Not all of them, but most of them. So we've got some red hash marks along the top and the sides here, and some blue hash marks at the bottom. Usually where the color was the most dramatic. Again, to show it. Blue and red and blah blah blah. But what does that mean? Well, check it over here on the right-hand side. You'll notice that some of these are red and some of these are blue. In fact, there are the same number of bars that are red as there are over here, and there are the same number of bars that are blue as there are, blue cells over here. These are showing you where the bridge fails. If a cell is colored, that value is above 1, and the bridge will fail at that point. The higher the number is, the more dramatic the failure. So you'll notice that, these ones on the bottom more or less stayed the same, and their tension force, blue represents tension, is fairly low. Well, it looks like we got 1.05, 1.01, and 1.05 again. Very, very close to 1, just a little teensy tiny bit over. And then over here, like if we use the selection tool, it will highlight it over here on your screen. On mine it's not going to because, we've been through that whole song and dance. But anyway, if I refresh the screen, you'll see that 42 down here is highlighted, and 42 is the one I clicked on. And this compression force, red is compression, blue is tension, so this compression force is 1.47, which is it's kind of bad. Probably shouldn't be that high. If we click the one at the top here, we already know the answer to this. 23. 23 is the one that's 1.86. We got pretty close to 2, and if you recall, that's the one that bent. Those are the bars that bent in the middle. So that's a pretty dramatic failure, and as you'll notice, we've got a big fat red sign with the line through it denoting that we did something wrong. So, we didn't exactly succeed. That's okay. We can do something about that. Let's spend some time looking at what exactly we can do. Fail. So now you can see, the members that failed and why. The ones with the red slashes failed due to compression forces, and the one with the blue slashes failed due to tension. So the first thing we're going to try is thickening these bars on the edges. So I'm going to click on this one, number 42 over here, and I'm going to hold down Control, or you can hold down Shift, and click member 28 over here on the right-hand side. Now, these aren't going to be named or numbered the same because a large part of that is down to what order you drew these. So, the leftmost one and the rightmost one that failed due to compression. So now I'm going to bring your attention, after selecting those two, to these 3 drop-down menus up here. We've got one that's labeled carbon steel, we've got one that's labeled solid bar, and we've got one that's labeled 140 by 140. I wonder what those could be. Maybe, I'm just spitballing here, maybe they have to do with the properties of these bars. So the first one, carbon steel, is the type of material it's made out of. We'll worry about that one in a moment. We'll keep it at carbon steel for now. The second one we'll take a look at in a minute, and the third one is the one we're actually interested in. We're going to up this to, I believe, 160 by 160? 150 by 150. Let's not jump the gun here. So 150 by 150. So we're going to keep it at carbon steel, keep it at solid bar, and we're going to go from 140 by 140 to 150 by 150. And you should notice up here that this is iteration 2, and our bridge cost has gone up a little bit. So let's go ahead and simulate this again. Bad things happen still. Truck still refuses to go across. There's still a failure on these two, but you'll notice that it's lower. So what if we upped it to 160 by 160 and ran it again? Still a failure. Still badness, but look, we don't have the red cells here anymore on 28 and 42. These are now below 1. So what have we done here? What do you guys think we've done here? I might have already explained it, I can't remember. I don't know. But what do you think we've done here? Okay, that's okay. All we've done here is we've increased the size of the bar. We've made it thicker. So when I say 160 by 160 or 140 by 140, what I'm referring to is the cross section of the bar. So this is the bar looking at it head on, as opposed to, from the side like we have been looking at it. So this is head on. So when we say 140 by 140, we mean that the width and the height of the bar are both 140 millimeters. That's all. Just they're both 140. So by upping it to 160, boom, 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 that is already way bigger than, 160 by 160, but who cares? We've made it thicker. So by extension, we've made the bars, those individual bars that we made 160 by 160, stronger. Now, how exactly does the math shake out on this? Because you can think in your head like, okay, if we reduce this to like tree twigs or something like that, a really thin twig is going to be easier to snap than a really like thick tree branch or like a tree trunk. That's not, you can't really snap a tree trunk barehanded. That's not really a thing that humans do. It's certainly not something they're known for. So we know intuitively that thicker objects are going to be harder to, bend or break. But in order to go over this math, we're going to have to understand a couple of concepts first. So the first one is inertia. Now, inertia is basically the quality by which a mass or matter moves and continues to move, or rests and continues to rest, unless it's acted upon by an external force. So, you get on a skateboard, you ride down a hill, and that skateboard's still moving even after you reach the bottom of the hill, right? Like you're still going with some decent speed. That's inertia. Now, it should be said that, when you're driving a car, you need to constantly burn fuel in order to move. When you're flying a plane, you need to constantly burn fuel in order to move and stay in the air. When you're running, you have to exert force in order to keep going. If you ride that skateboard down the hill, eventually that skateboard will stop. That's not going to be the case if something's out in space. So, like, let's say you take a baseball and then you just sort of like throw it off into deep space somewhere. That baseball is going to go forever. Assuming a couple of things. It doesn't run into a planet or a sun or something like that, and it doesn't get caught in something's orbit. But what are we saying in that sense? All we're saying is that those things are external forces acting upon it. The reason why planes need to burn fuel constantly, the reason why cars need to burn fuel constantly, the reasons why you need to burn fuel constantly in order to keep moving, is because there are always forces acting upon you. Friction is generally the most common one. A little bit of energy is lost from the bearings and the wheels, or the air molecules hitting the surface of an object. That's more drag than it is friction. But regardless, drag and friction are both forces which act upon something and slow it down, thereby eliminating its inertia, or changing its inertia, I should say. Now, the second important I'm sure you guys are already familiar with inertia, but I figured I'd just explain it just in case. Now, the second thing is the moment of inertia is a quality that a body has. And it's a quantitative thing, so it's a thing expressed in numbers, and it expresses a body's tendency to resist change. Well, what do you mean by that? So, a moment of inertia sort of describes in numbers how hard it is to change an object's inertia. So you think of it in terms of that skateboard again. That skateboard, it starts going pretty fast as soon as you, like, you're sitting at the top of the hill and you just kind of tip it a little bit and you start riding down with it. That skateboard's already going about as fast as it can go pretty early on in that ride down the hill. When you reach the bottom, the skateboard goes a certain distance. You can, once it, like, you can have something like a bunch of cardboard boxes or something like that to break your speed or whatever, and it stops the skateboard. I don't recommend trying this at home, by the way. I'm just using this as an example. But, you can use some cardboard boxes and sort of break your movement, and that's that. The skateboard has stopped, and the inertia has been destroyed. Now, or changed, rather. Now, this is completely incorrect to say it's been destroyed. Now let's say you have a school bus. You're sitting at the top of that same hill. And you tip the school bus. The school bus might take a lot longer in order to reach speed as it's going down that hill. On the other hand, when it reaches the bottom of that hill, assuming there isn't like a ton of drag or friction acting upon the bus, it's going to take some serious work to keep that school bus from continuing. You can't just throw down some cardboard boxes and have the bus stop. It's going to plow through those and it's going to keep going. And even if you didn't throw anything down on the ground to impede the progress of anything, that school bus would travel further than the skateboard. I mean, generally, again, assuming the same amount of, the same amount of friction acting upon both of them. Same amount of friction, same amount of drag. It might be that the bus experiences larger forces upon it. It has more drag because it's a larger object, more boxy. It might have more friction because, the wheels are of a lower quality, that sort of a thing. And so it might, slow down just as fast as the skateboard does, but that's certainly not because, it's being acted upon with the same amount of force. Because that wouldn't be the case. So anyway, a moment of inertia is basically how hard it is to change the inertia of an object. In so many words. That can be expressed with an equation. So the moment of inertia is equal to the base of the object times the height of the object cubed. So you cubed the height of the object and you multiply it by the base and then you divide it by 12. And that gives you the resistance of a body to change. So now maybe you can see how much increasing the cross-section of one of these things by 20 or even 10 can change so much. Because this stays 12. This is always going to be 12, always and forever. And this is going to increase linearly. So that's going to increase by 10. When we increase it by 10, blah, blah, blah. We increase this by 10. This value increases by, a 1,000-fold. Sort of. I mean, 10 cubed is 1,000. Let's just put it that way. 10 cubed is 1,000. So there is a much larger change when things are, increased linearly. For example, the 140 by 140 millimeter bars that we have, the moment of inertia is about 32,013 newtons, more or less. An object that is 150 by 150 millimeters, so we've increased, the cross-section by 10 millimeters on each side. That rockets up to 42,187. So that is 10,000 more than the previous one, which 10,000 is a large number, but it should also be noted that that is a third more by increasing it by 1/14th. Each dimension by 1/14th, I should say. We've increased the moment of inertia by 1/3. The area is increased by more than a 14th, but, it's actually maybe less than that. Yeah, anyway. But you'll notice there is in fact more. But you'll notice that the moment of inertia only takes in base and height. Nothing denotes type of material. So this moment of inertia, is that the same for wood as it is for concrete and steel? I don't know. So enter two more things, yield stress and modulus of elasticity, where the type of material becomes just as important as, its size in order to determine, its resistance to change. And we'll go into that later. Um, Now, if we calculated all this stuff on our own, things are going to be different from how the program puts things out. Because what we're going over right now, like, you guys don't have to memorize this in order to use this program. I'm not expecting you guys to know all this stuff. I just want to show it to you so you have a general idea of some of the behind-the-scenes stuff that goes on in the program. And, if you ever get interested in civil engineering and bridge building, this is the kind of stuff that you'd be dealing with. Well, I take that back. Nowadays, you'd be dealing more with this kind of stuff. But back in the day, you would have done with that, and you would have dealt with that to some extent. And if you were writing a program like this, you would be dealing with that, those equations, I should say. So let's do something else. Yeah, let's do that. Okay, so let's take all of these bars up here which failed along the top. We're going to do two things. First off, we're going to change it to 160 by 160 like all the other ones. And then we're going to change from carbon steel to quenched and tempered steel. And let's see here. Let's go ahead and run the simulation again. And look at that. That is dramatic, and the bridge fails. Uh-oh. But look, it didn't fail immediately, upon start. So let's go ahead and we will let's change these to 160 by 160. And let's see, that doesn't improve anything. Dramatic, 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 and failure points. Alright, so it looks like we're probably going to have to worry about the bottom bits here. And let's change those to quenched and tempered steel, because that's more relevant to the next thing I'm about to go over. And success! So what we've done is we've changed these top bars, the ones that failed before. We replaced them with quenched and tempered steel and changed the cross-section to 160 by 160. We changed these two bottom ones on either side of the middle that failed due to tension and made them quenched and tempered steel. And then we thickened these two on the edges and made them 160 by 160 but kept them at carbon steel. With all of those things, we made a successful bridge that looks like something I would never want to go across. But it works! It certainly works. Look at it go. If we had a second, truck drive by, like right now, you would see that at least we kept some sort of consistency with it, so the bridge doesn't fail, thankfully. But yeah, so that works. So now the material changes things. Let's spend a minute looking at what might be the best material. So, you guys, here's a question. Where is steel on the periodic table? I'm sure you guys know this already. Okay, so we got one vote for ST. So ST, if I remember correctly, if that is here, no, because SR is strontium. Well, anyway, just so you know, it ain't. It's actually not an element. It is an alloy. So an alloy is a metal made by combining two or more metallic elements to give greater strength or resistance to corrosion. Steel is a combination of two elements at its most basic level. And those two elements are iron and carbon. That's all steel is, it's just a combination of those two. So stainless steel is a variant of steel, and it comes in many forms, but the main element in stainless steel is chromium. It also has nickel and nitrogen in it, though, which is kind of interesting to me that nitrogen exists in steel, like it actually helps to strengthen the bonds. And so carbon steel is the steel that's used on most of these parts of the bridge. Oh, this good old lovely bridge that sort of renders bit by bit as I move my cursor over it. But yeah, carbon steel right here. Carbon steel is the most common grade of structural steel, and it's generally about 0.25% carbon. So that is to say, it's not even 1% carbon. There is a whole lot of iron in the steel, and there's a little teeny tiny bit of carbon. Now, it should be noted that there are many grades of carbon steel, but generally, carbon steel has 0.25% carbon. That stuff costs $692.37 per meter. Per meter. So it's pretty expensive. So high strength, low alloy steel. The high strength is obtained from small amounts of manganese, niobium, formerly known as columbium, and vanadium. So, interestingly, niobium, formerly known as columbium, was also known as tantalum because they were both discovered by the same person at the same time. Well, not really at the same time, but they didn't realize that they were the same element, and anyway, just a whole confusing thing. Anyway, that one is $796.30 per meter. And then finally we've got the quenched tempered alloy steel, which is similar to the high strength low alloy with the niobium and the manganese and the vanadium. However, it undergoes a special heating process, which happens after the metal cools. So basically the temperature and the amount of time it is heated is precisely controlled, which changes the chemical structure, the lattice structure of the actual material, strengthening it. And by lattice structure, I mean literally how molecules are all connected to each other. So, you know, increasing the strength of the metal on a molecular level, the alloy on a molecular level. But that one's expensive because it's pretty process intensive. It costs $853.92 per meter. So each of these materials has a yield stress, elasticity, and plasticity. So yield stress is the indication of basically how much it can take before a metal starts to get deformed, bent, like what we have in our lovely little simulation in the beginning. Elasticity is the tendency of solid materials to return to their original shape, so basically bend and then go back to how they were, like rubber bands. However, plasticity is the tendency of solid materials to bend or whatever, deform, and not return to its original position. So, like silly putty versus, in this example, a rubber band. So rubber band is elasticity because you can pull on it, stretch it out, it will return back to its original shape. Silly putty has plasticity because you can, you know, deform it and it will hold that shape. Generally, depending on the shape that you create. But yeah. Here's some more math and yield stress. We're not even going to worry about that, just because explaining the the lambda and the phi and everything like that. I'm not really going to get into that right now. So everything passes. Now we can do one more thing. One more thing. In order to mess around with our bridge design. Let's try taking these two bars close to the end, not the very end bars, but the ones close to the end, and we'll change it to hollow tube. So that's that second drop-down list. We've got solid bar and hollow tube. And let's hit simulate. Oh, immediate failure. Well then. Let's go ahead and change the dimensions on those two to 240 by 240 by 12. So now they should look a whole lot thicker. And if we run the simulation, there's some drama, but it might actually live. It might actually live, and it does. Look at that. Boom. And if we look over on the side, we've got no, stressors on it or anything like that. No red, no blue. But why did we do that? Why did we do the hollow tube? And what did we do? Well, those are some excellent questions. So literally what we've done in this simulation is we've changed, maybe member details has a little bit more information that we can look at. So if we click on this end bar right here, sorry I keep doing that, it's just I'm forcing the screen to update whenever I move it from the top of the top of the screen back down and then back up. As you can see, this is the cross section. So this is the diagram I was doing here, this lovely diagram that I had. The computer's done it much better than I have. But this is what the the bar looks like from the side, 160 by 160. Now let's click on this one. Hey, look at that, it's hollow in the middle. So that's exactly what hollow tube means. We've cut out all of the middle material, we've made it thicker overall, but we've cut out all of the middle of the bar. So, why would we do that? And there's a pretty big hint for you right there. We would do that to save money. Look at that, just those two bars with solid carbon steel, from solid to hollow carbon steel, drop the cost by $6,000. Of course, there is a trade-off between strength and money, so those parts did become weaker. It's true. But, by the same token, we dropped the cost of the bridge something fierce. Not really something fierce, but, decently. Change the material. So, when this slideshow was made, after 51 iterations, total cost of the bridge was $383,000. Roughly. More or less. The one I just made is $374,822. So we've already proven that there are a couple different ways to go about making a bridge cheaper. Type of material that you use, the way you go about it, all these things. So now, part of your guys' challenge is to make an even cheaper bridge. Cheaper than $374,000. I believe in you guys, you could do it. Now there's one more thing. I wanted to talk a little bit more about this member details part, because that's actually, that's pretty handy. So you'll notice that the material is listed as carbon steel, all this stuff, blah, blah, blah. That gives you the basic sort of information on the strength of carbon steel, including the yield stress, the modulus of elasticity, the mass density. So modulus of elasticity being, how far it can bend and still return to its normal state, and the yield stress is how much, before you start to plasticize the steel. the cross-section type, the cross-section size, the area, the moment of inertia, hey, that should be familiar, and the member length being the length of the actual thing on the bridge. And then you got the unit cost, which is, the amount per meter, and you'll notice is pretty significantly cheaper. And the member cost, yeah. And then you got this graph right here. So the graph is essentially based on the length in meters from 0 to 12, how many kilonewtons of force it takes in order to bend it. From, 0 meters being about, what is that, 2475, 2490, something like that, 2475. 2475 kilonewtons of force in order to bend it. And then it goes down pretty linearly, sort of, kinda. It's more quadratic or logarithmic, I suppose. I don't know. It's hard. It's a very smooth curve. Um, until we're at about, a little bit below 6, and we're actually looking at a slightly lower one because it's hollow, but, um, about 18 to 1900 kilonewtons of force in order to bend it. So you can look at that kind of stuff, mess with the length and everything like that in order to get an idea of, you know, what, how you could reduce the amount of materials required and also increase the strength of the bridge. On top of that, you can mess with the cross sections, the type of material it's made out of, everything like that in order to bring these values within acceptable ranges and reduce the cost of your bridge. So you just keep iterating on it and, testing it to ensure that you got a working bridge that's as cheap as it can possibly be. And of course, if you click on the calculator here, it will expand this stuff so you can take a look at everything that's going into the cost of your project so you can reduce costs where necessary. So you start it over and then organizing the data, blah, blah, blah. That's one more thing. Slenderness is a ratio between the length of the piece of, or length of the member and the thickness of it. So you got to make sure that the slenderness stays below 300, because otherwise it's that you're going to have a bar that's way too weak. Yeah, so perfect. Slenderness ratio is length divided by radius. You can also go into the help, how to design a bridge in the bridge design window, and these will go over all the stuff you need to know in order to, and there's a bunch of different, there's a bunch of different materials, and by materials I mean things to read. That'll go over all the different things, the mathematical concepts behind bridge building here. And you can be as in-depth or, as superficial as you'd like. I don't mean superficial in a bad way necessarily at this point. I just mean guess and check, as opposed to actually going into the math and figuring it out the long way. So it's about as much investment in it as you'd like to put into it. But yeah, at this point, it is 8:55. So I will ask the poll questions, and then, we can leave it open for question and answer, or work on your bridge, or head out, or whatever. And if you head out, we'll just see you on Monday.